In this video, I'll go over dilations. This is really going to focus mostly on what a dilation is, and then in the second half of this video, we'll go over mostly how to use the scale factor. How to use the scale factor. Dilation just means to change size. When we change the size, the shape will still stay the same though. Since this is a same size, or same shape and different size, congruence is not preserved. If my pre-image and image are different sizes, they cannot be congruent because congruent means same shape, same size. However, the angle measures will remain equivalent or equal. Orientation, or how the shape is facing, is preserved in dilations. So if I've got a shape pointing up as a pre-image, in my image it'll be smaller, but it'll still point up. Or if I've got a pre-image, small arrow pointing to the this is left, my image will still be an arrow pointing to the left, it just might be larger than. To dilate a figure, we're just going to multiply every coordinate by the scale factor. We're just multiplying everything by the scale factor. Oops, sorry. I wanted to highlight that. If the image is larger or bigger than the pre-image, the dilation is called an enlargement. Large makes me think bigger or larger. An enlargement is when my shape is bigger, the image is bigger. If the image is smaller though, the dilation is called a reduction, which would make me think of the word reduced or smaller. The pre-image and the image are similar figures. Similar figures means that their sides might not be the same size, but they are proportional by that same scale factor. Proportional by the scale factor. Their corresponding angles, since dilations do preserve the angle measures, their corresponding angles are congruent or equal in size. For an enlargement, the scale factor is bigger than 1. For a reduction, the scale factor is less than 1. Oh, that's not what I wanted to click on. Gonna fix this. Much better. Okay. The general rule for dilations is kx, ky. K, or what we're multiplying by, is the scale factor. So you can see we just multiply the x and the y values by that scale factor k. It might be worth noting we start at a normal ordered pair x comma y. This transforms or changes to kx, ky. We're just going to look at some examples of what a dilation looks like. I know it's kind of hard to see. This 1, 2, 3, 4, 5 pentagon is A. This pentagon is A prime. And this semicircle is M, and the one on the top is M prime. So here, my pre-image is A. A is larger or big. And my image, that's the one with the prime notation, A prime, is smaller. That means this was a reduction because the image got smaller, or the image is smaller. The pre-image got smaller to get to the image. In the next example of this, just a picture of this, I start at my pre-image, which does not have the prime notation. Pre-image. That's this one, which is smaller. M is smaller. And the image, which does have the prime notation, is the top semicircle, which is bigger. So I know that since I got bigger, or when the semicircles got bigger, this was an enlargement. I know that this is an enlargement because the image is bigger. Next, we are given that the scale factor is 3. I want to know, is this an enlargement or a reduction? If we look at the top of our notes, we have an enlargement if the scale factor is bigger than 1. It's a reduction if the scale factor is less than 1. So we're going to compare the scale factor and 1. We're comparing that same scale factor, 3, and 1. 3 is larger than 1, which means this is an enlargement. If I were to write the algebraic rule, I'm writing an ordered pair, but I multiply each x and y by whatever the scale factor is. My scale factor is 3, so I'm writing a normal ordered pair, x comma y, except I multiply each coordinate by the scale factor, 3. And the second, the one to the left of this, to the right of this, directions are hard. We've got that the scale factor is 1/2. To figure out if this is an enlargement or a reduction, we compare 1/2 and 1. 1/2 is smaller than 1, and you can verify that if you don't like working with fractions. You can type this in on the calculator to see that 1 divided by 2 is just 0.5. And 0.5 is less than 1. Now, since my scale factor, 1/2, is less than 1, this has to be a reduction. The algebraic rule is going to be your normal ordered pair, x comma y, but you'll multiply each x and y by whatever the scale factor is, or 1/2. In the enlargement, we're going to multiply every coordinate by 3. If we're multiplying our coordinates by 3, our numbers are going to get larger, which means our picture also gets larger. That's why I know if the scale factor is larger than 1, it's an enlargement. For our reduction, 1/2 is a number that's smaller than 1, but still bigger than 0. When I multiply any number times 1/2, it'll get smaller. Since my numbers are getting smaller, so will my picture. Which is how we know that when we multiply by a positive number less than 1, we get a reduction. Using that information, I'm just asking you guys to write your own rules for a reduction and enlargement. For a reduction, you're just going to pick a k that is less than 1, so you can use something like 0.3479. You could use something like 6/7. You could use 3/8. any of those work. You just take whatever you're using as K. I might use 7/9. Multiply that by both the X value and the Y value. For an enlargement, you just need to pick something that is larger than 1. You could use 49,602. You could use 7. You could use 3.5. Whatever you pick, I'll use 14/3. Whatever you pick, you multiply by X and also Y. To draw an enlargement, the shape that you draw, I'll pick a rectangle, call that A. I have to make my image, or A prime, that same shape, but bigger. To draw a reduction, we'll start with a shape. I'll call that T. The image, T prime, has to be smaller than what we started with. The triangle gets smaller in the image, so this is a reduction. The rectangle got bigger in the image, so that was an enlargement. This algebraic rule is for a reduction because 7/9 is smaller than 1. This algebraic rule is for an enlargement because 14/3 is bigger than 1. If you don't like working with fractions, you can take out a calculator and verify that those numbers are truly smaller and larger than 1. The bulk of today's lesson is really on the back of this page. We want to write the pre-image coordinates from this graph that we're given here. A is located at 0. I didn't go left or right at all, so that's a 0, and then down 2. Down 2 is -2. So A is at 0, -2. B is left 1, up 2. Left is negative, so B is at -1, and up 2 is positive, so +2. C is to the right, 1, 2, 3, and up 1. Right 3 and up 1 are both positive, so C is at +3, +1. Side to side first, then up and down. They tell us that the rule is x, y transforms or changes to 2x, 2y. Since I'm multiplying by 2, the scale factor is 2. To know if this is an enlargement or a reduction, we'll compare the scale factor, 2, and 1. 2 is larger than 1, which means I should have an enlargement. This is the part we haven't looked at yet, going from our pre-image coordinates to our image coordinates. To do that, we'll simply just multiply each coordinate by the scale factor. So we're multiplying the x values and the y values by the scale factor, which is 2. 0 times 2 is 0. So A prime's x value is 0. A prime's y value is -2 times the scale factor, 2. -2 times 2 is -4. To find the image coordinate for B, or B prime's ordered pair, I take each coordinate x and y and multiply it by the scale factor, 2. -1 times 2 is -2. 2 times 2 is 2. Oh, sorry, 2 times 2 is 4. 2 times 2 is 4. To find C prime, take a minute and pause this video and see if you can't get that on your own. To find C prime, we take each coordinate and multiply it by the scale factor 2. 3 times 2 is 6. 1 times 2 is 2. Now that we have our image as coordinates, we can put that on the graph. A prime is at 0, negative 4. So we don't go left or right at all, and to get a y value of negative 4, we go down 4. I call that A prime. B prime is at negative 2, positive 4, so left 2, up 4. It's B prime. C prime is 6, 2, so that's right 6, and up 2. Then we can just connect the ordered pair, or the ordered pairs. And we see that our triangle is the same exact shape, just way larger. We have the same shape. The sizes, it's not the same, it's larger. So I'll put the size is different. The orientation, notice, is the same. If I draw an arrow pointing to A in both of my triangles, my arrow points down. If you're looking for orientation of the vertices, we start at A and read clockwise, A, B, C, A, B, C. So the orientation is the same. Congruence cannot be the same because the size and shape are not both the same. Since the size is different, the congruence is also, congruence does not hold. The congruence is not preserved. Let's say it's not congruent. On the homework tonight, it might be worth noting, you'll be asked to write the pre-image ordered pairs from a graph. It's going to be backwards on the rule and the scale factor. You'll be given a scale factor and you'll have to produce the rule. Then I'll want the image coordinates and I need you to plot the image on the graph as well. That's all there is to using a scale factor to working with dilations. You simply are just multiplying each coordinate by whatever the scale factor is to produce the dilation, smaller or larger. Looking at the second example here, I need the pre-image ordered pairs. So I'm reading K at left 1, 2, 3, 4, down 1, 2, 3, 4, 5. So K is at negative 4, 5. Negative 5. Negative 4, negative 5. L is at right 1, 2, down 1, 2. So L is at 2, negative 2. M is at 1, 2, 3, 4, 5, 6. To the right, 6 right, and 1, 2, 3, 4 up. So M is positive 6, positive 4. And N is left 1, 2, 3, 4, 5, 6. Up 1, 2, 3, 4, 5, 6. So N's ordered pair is negative 6 because we went to the left, positive 6 because we went up. The rule is half times x, half times y. So the scale factor is just 1/2. One half compared to 1, 1/2 is smaller than 1, which means this is going to be a reduction. To obtain the image coordinates from the pre-image coordinates, we'll take our scale factor and multiply every coordinate by the scale factor. So we're multiplying negative 4 times 1/2, negative 5 times 1/2, 2 times 1/2, negative 2 times 1/2, 6 times a half, 4 times a half, negative 6 times a half, and positive 6 times 1/2. So K's ordered pair, K prime's ordered pair, sorry, negative 4 times 1/2 is negative 2. Negative 5 times 1/2 is negative 2.5. Or half of negative 4 is negative 2. Half of negative 5 is negative 2.5. L prime, 2 times 1/2 is 1. Negative 2 times 1/2 is negative 1. M prime is located at 6 times 1/2, which is 3. 4 times 1/2, which is 2. N prime is located at negative 6 times 1/2, or negative 3. And then 6 times 1/2, or positive 3. Now we have all of our image ordered pairs, so we can put this on our graph. K is at negative 2, negative 2.5. So left 2, down 1, 2, and between down 2 and 3 is negative 2.5. So here is K prime. L prime is at right 1, down 1, positive 1, negative 1. M prime is positive 3 to the right, positive 2 up. N prime is at negative 3 to the left, positive 3 up. And now we can connect those ordered pairs, those points. And we see the same shape, but the size is different. It's smaller now. Since the shape and size are not both the same, these quadrilaterals are not congruent. If I had an arrow pointing to K in both the pre-image and the image, my arrow is pointing kind of down and to the left. The orientation is the same. I want to point out, we used the scale factor to decide if this was going to be a bigger image, or a smaller image before we even had our points plotted. So this is a good way to check to see if you're at least on the right track. If you have questions or concerns about the content in this video, please send me a Schoology message, an email, or drop a comment on this video, and I'll get back to you as soon as I can.